screen shared here, and then I'll get things moving. So bear with me 1 second. So I'm assuming everyone can see my screen at this point. Just give me a thumbs up or a yes if you could.
Yes. Yep.
Yep.
Okay. All right.
Yes.
All right. So I think it's time to get going. I have a little bit after 12 here, so in the spirit of keeping things moving, we'll get started here. So today we're going to be talking about and polyfluoroalkyl substances, collectively known as PFAS. And for those of you who don't know me, my name is Tim Woods. I'm in the PM group, and I have over 20-year history in the RI component of investigations, and in addition to that, I'm a human health risk assessor. So everything you're going to hear today would be coming from that perspective. So just keep that in mind. A lot of people on this call here have probably heard of PFAS. It's a pretty big issue going on right now in our industry, and our client, i.e. the DoD in my case, they have a really big problem with it. So this presentation is intended to present what we know about PFAS at a relatively high level at this time, understanding that the area, the technology, the regulations are changing somewhat rapidly with PFAS. So again, this is a snapshot in time, and as processes evolve and we get new sites to work on or new contracts, you always want to see what's the most up-to-date information with regards to PFAS. So that's a real quick introduction, but before I jump into this, I'm going to throw it over to Natalie, and she's going to give us some logistical information, and then once she's done with that, we'll start getting through the slides, and I'll show you how this presentation is going to go. So Natalie?
Great, thank you, Tim. So just real quick, we are recording this session for those of you who hadn't heard at the very beginning, but we will be recording it. We will be posting it to Talent LMS. You all will get credit for being on the call here today. I'm going to just run an attendance. So this will actually be uploaded to Talent LMS. If you get a message that says you've been assigned a course, but it hasn't shown as complete yet, just give me a little bit of time to make sure I get all the records in, but you will show complete. For those of you who are calling by phone, just make sure that you send me a message to let me know that you were on the call, because if I don't, I just see your phone number, I don't see your name. But that's pretty much all my spiel, and I will turn it back over to Tim.
Okay, thanks, Natalie. And now, fair warning to all, there will be a quiz at the end, so just keep that in mind as we're going through here.
Yes, thank you.
All right. So the presentation is organized as follows. We'll talk about the background. We'll talk about the current regulatory status, treatment options, disposal options, what the DoD's ultimate position is, or at least their current position is, and where our current and future opportunities lie with PFAS. I'll be your lead here. I'll be talking about items 1, 2, 4, and 5. Mike Klosky will be talking about the treatment options, and Doug McClure is going to wrap up the presentation and talk about our item number 6, our opportunities. So if there's any questions along the way, just if you don't mind, just hold off. At the end, we do have a Q&A session. And if there's anything that you feel is a really kind of detailed question that you think warrants direct conversation with me or Doug or Mike, we're all available to answer those offline should you want to handle it that way as well. So with that being said, we're just going to keep on going here. Just a couple important acronyms that you'll probably see throughout the presentation are listed here. I'm not going to say much about this other than just keep this in mind as we're moving forward. So our background for PFAS is an interesting one. It's a suite of man-made chemicals. There, as of right now, you see varying numbers of how many there are around or exist. What I've seen is about 5,000 different types of PFAS, some of which have been more widely used and studied than others. What we're really concerned with uh, are PFOA and PFAS. These are the compounds that initially drew regulatory attention, and a big component of why that happened is because the analytical procedures really allowed laboratories to see these compounds at really low levels. So could someone go on mute, please? Thank you. So the whole impetus behind this issue was these new analytical procedures that really were able to get to really low levels. And we'll talk about that more a little later on in the presentation. But collectively, the PFAS family of compounds, they're resistant to grease, oil, water, heat. They've been widely used in various products that I'm sure we all have used at one point in our lives or another since the 1940s, believe it or not. And what I'm referring to there are stain and water resistant fabrics, carpeting, cleaning products, paints, firefighting foams, and a whole suite of other things that aren't listed here. But what's interesting is that given the focus and the concern that we are collectively as a country seeing with PFAS, is that certain PFAS are still authorized by the FDA for limited use in various cookware, food packaging, and other related products or activities. So the problem with PFAS is that it's essentially detected within the blood serum of the general population. I've seen estimates up as high as 95% of the population has some level of PFAS in their blood. So that's a bit of a problem, I'd say. But what we're seeing is that some groups may be exposed to higher levels as a result of the occupational settings. And the two examples I'm showing here are firefighters and military personnel. And essentially, the military personnel are those that are involved in fire training or firefighting activities through the use of firefighting foams. As I'd mentioned, PFAS has been documented through blood tests in humans and in animals. Right now, the current science is telling us that it's an issue in the groundwater for the DoD, at least for now. That's certainly subject to change as we learn more about this class of compounds. On a personal level, I was involved in an exposure assessment back in the mid-2000s at a PFAS production facility in northern Alabama. And as part of that investigation, and this, you got to remember, this was back before PFAS were a commonly known issue. But even back then, we found PFAS in all sorts of environmental compartments, ranging from soil to sediment to surface water. It was a production facility, so we had air emissions. But we also found it in fish tissue. Downstream of the facility, we found it in vegetative products like tomatoes, greens, things like that. And we also found it in animal products, such as waterfowl and beef and dairy cattle. The point I'm making here is that once this stuff is out into the environment, it gets everywhere. And once it's in those different environmental compartments, it presents a whole host of issues to, number one, characterize, and number two, address. So I've been talking about PFAS. Let me just break that down a little bit better for us here. So think of it as the PFAS family, and this graphic here demonstrates that. I got this from the ITRC guidance document, and for those who are interested, they do a great job with their guidance documents. And if you have a real interest or concern at one of your sites, that is a pretty good guidance document to be aware of and to have download to your hard drive and take a look at. They do also offer a number of YouTube videos of various presentations that I would encourage you to have a look at. But back to this slide. So under PFAS, you have what's called the non-polymers and the polymers. Let's just put the polymers off to the side right now. That's really not germane to what we're talking about. We're going to focus on the non-polymers. And here under that, you see two branches of the tree. You have the perfluoroalkyl and the polyfluoroalkyl. The difference between those two categories is that the perfluoro is essentially the fully fluorinated carbon chain. And the poly is not, it's a fluorinated chain, carbon chain, but it's not fully fluorinated. It's a subtle difference, but it's not really, it's just for your informational purposes right now. We're really going to focus on the perfluoroalkyl substances. And under that part of the tree, we see the perfluoroalkyl acids, also referred to as PFAS. And underneath that, we have the carboxylic acids and the sulfonic acids. Those are the two categories that we really are concerned with here. The carboxylic acids is a fancy way of saying the PFOA, and the sulfonic acid is the fancy way of saying the PFOS. And as I had mentioned earlier, we are really focused. While all this stuff's really interesting and cool, we're really interested for the purposes of this presentation and what we're contending with on our sites are the perfluoroalkyl acids. So let's take a closer look at what that means. This is this is the chemistry portion of the presentation. I don't think there's a question on the quiz about this, but just pay attention, just for fun. What you see here are up top, you see the perfluorooctane sulfonate, PFOS, and you see a head and a tail. And you see the same thing for PFOA. Again, you see the head and the tail. In both cases, the tail is a fully fluorinated carbon chain. It's their octanoic acid, so you'll see 8 carbons. What separates these two acids is the functional group that's at the head of the tail. For the PFOS or sulfonate group, or the functional group for the PFOS is a sulfonate group, and the functional group is a carboxylic group for PFOA. And these are the charged functional groups, which gives it these chemicals or acidic properties. What's really important about the PFAS, the perfluoroalkyl acids, is that these are considered terminal substances, meaning that these are the end products of degradation processes. And it's essentially saying these things are non-degradable under normal conditions. That's a big problem. So I just gave you the background, a pretty high level background, of course. Now we'll transition into talking about the regulatory status. And here I'll talk about essentially 2 components. Number one, where the federal government stands at this point in time. And number 2, where the various states stand at this point in time. So up first, we'll talk federal. PFAS is largely unregulated at the federal level right now. There are no MCLs that are your promulgated standards. However, there is a health advisory level that was released in 2016 by the EPA for drinking water exposures, and that level was set at 70 parts per trillion. So just keep that in mind. We're talking parts per trillion levels here. For all the contaminants I'm used to dealing with, you're in parts per million or parts per billion. We're talking about really, really low levels here. But they said,
I'm sorry, Rob. What was that 70 part per trillion based on?
I will show you that, August, in I think 2 or 3 slides. I have a breakdown on how they got to that number, but that's a good question.
Thank you.
You're welcome. So what this number represents, 70 parts per trillion, it's either for individual PFOA or PFAS or PFOA, PFAS combined. It's a subtle difference, but it's something that you just need to be aware of when you're looking at data at a given site to see if there's an issue or not. The link I share here shows you where you can go online to EPA's website and find some more information about this health advisory level. It is worth noting, however, this is currently the non-binding standard for PFAS at our federal government level. So there was some good movement in March of this year, where EPA announced its preliminary determination to begin to regulate PFOA and PFAS under the Safe Drinking Water Act. They saw comments on a number of issues here. I'm not going to read through them. You can certainly do that. But the comment period ended on May 11th, 2020. And I haven't heard anything subsequent to that. I just knew that they started the process, and that's about it. A lot of our sites, when we're looking at contaminants and contaminant exposure and things like that, fall under CERCLA, and we need to evaluate contaminants accordingly. PFAS are not identified as hazardous substances yet by the EPA, but in a number of circumstances, they could be and even have been responded to as CERCLA contaminants. And I'll point to a couple examples that a number of folks on the phone are aware of when that happened. Most recently, work that we were just awarded out at Fort Hunter Liggett and Joint Base Lewis McChord to perform remedial investigations for these compounds. The direction is to evaluate them as if they're CERCLA contaminants. And that's not uncommon. We've seen that at other sites, Fort Leavenworth, Kansas, and other sites throughout the country. But believe it or not, the whole take-home message here is that the federal action on PFAS has been slow to develop, which I think we all know how that goes. There's political powers at play. There's stakeholders at play. So it's been slow, but I think there will be movement, hopefully within the next year or so. So we'll see where that takes us. Now to August's question, this is a breakdown of how EPA got to their health advisory level of 70 parts per trillion. What you see here in the green is the mathematics behind it. It's pretty basic stuff, but the important take-home points are the RFD, which is the reference dose, which is the measure of toxicity. And that, in this case, for PFOA and PFAS, is an animal-based measure of toxicity, which they extrapolate to human exposure. Okay. The second real critical piece to the development of the health advisory level is what's referred to here as the DWI. It's the drinking water ingestion rate. Okay. And in this case, it's based on water ingestion for lactating women. Now, we might think that's kind of a strange thing to do, but it's been identified that lactating women are a very susceptible subgroup for PFAS exposure. So when EPA goes about identifying how to set health advisory levels, they typically set them for the most susceptible populations. So that's what they did here. The next factor you see is what's referred to as the RSC, and that stands for relative source contribution. And this is pretty much a default term that is used to account for potential routes of exposure other than drinking water. Okay, so that's the basic premise behind the health advisory level. Again, if there's additional questions or you really want to kind of get into the weeds with this, I'm certainly more than willing to have some conversations or point you to different resources if people would like to take me up on that. One important note here, when you think about health effects, you think about cancer effects and non-cancer effects. By definition, a health advisory level is based on non-cancer health effects, okay? At the same time, EPA has determined, and you can see the quotations here, this is their classification, suggestive evidence of carcinogenic potential for PFOA and PFAS. However, they've deemed that this 70 parts per trillion level is protective of both cancer risks and non-cancer health effects. So that's basically where the federal government stands on the regulation of PFAS at the moment. Now we'll transition and we'll talk about where the states are. And what you see here on this map shows you all of our states, obviously. And what you see in green are states with promulgated standards. And what you see in, at least what looks like on my screen, is a maroonish color. They're non-promulgated standards or cleanup goals. If you recall earlier, I mentioned that this presentation is kind of a snapshot in time, given how quickly the regulations or the whole PFAS area is evolving. And I'll point to one example of that right now. Up in New York State, they had recently released MCLs, state-based MCLs, as of July 31st, 2020. So that is not reflected in this graphic, but it just shows you how quickly these things are moving. This graphic, I believe I obtained, it was dated, I think sometime in June of this year. So just keep that in mind. My advice to folks is, if and when you're working on a site and it's in a state, I would just be cognizant of if there's promulgated standards, but if not, are there promulgated standards that could be imminent that you'd want to consider when you're developing your approach and your proposal and your cost estimate and all that sort of thing. So just continuation of talking about states, this is just a sampling of potential standards or screening levels for various PFAS contaminants. Mostly they're for PFOA and PFAS, but you could see a few other ones in here that I haven't talked about. The take-home point here is, if you recall, I've been mentioning 70 parts per trillion. A lot of the states are going lower than that. You could see in California, for example, you're in single digits. New York, like I just mentioned, there are 10 parts per trillion. Again, it's just something you want to be aware of when you're working on your sites. This is not a comprehensive table, obviously, but I selected these states because a number of us either live in those or maybe doing work in those. When you have work on your own project, I encourage you to understand what that state is doing for regulations. Okay, so this, bear with me on this graphic. It's tough to read, I get that. But what it's showing is trends in PFOA screening levels. And if I had a similar graphic for PFAS, it would show the same thing. What you have on the y-axis are the concentration terms in parts per trillion. And what you have on the x-axis are various standards that have been released since the first one I'm showing here is 1991 through 2020. The point here is you can clearly see how the agencies are really getting restrictive on their various screening levels. Okay, just to me, this is showing us where the trends are, where they're going, and what type of liabilities we would be facing for our clients going forward. So this is the last piece of the regulatory presentation. Once I'm done this, I'll hand it off to Mike Klosky to talk about some treatment pieces. But here, the intent here, before I hand it off to Mike, is to show just what exactly is the extent of the DoD's PFAS issue. They're chasing PFAS or planning investigations in all 50 states, plus DC and 5 territories. So this stuff, they have a problem. You can see here a breakdown by branch, and what that is the number of installations. And you can also see here a breakdown by installation type: active, BRAC, National Guard. I did obtain this from an online resource, which I do have a copy of. It's shows every installation in much greater detail. So if anyone on the phone would like to talk about that or get a copy of that information, just reach out to me and I can get it to you. So now I'm going to hand it off to Mike Klosky to talk about some treatment technologies. And Mike, when you get going here and you need me to toggle forward on a slide, just give me the just let me know. So thank you, everybody.
All right, can everybody hear me?
I got you.
Okay, perfect. All right, Tim, why don't you move to the next slide?
Oh.
All righty. So treatment technologies are relatively well established, mainly based upon just DoD experience. That is just kind of a leverage off the, again, old technologies that we don't see an awful lot of, which is pump and treat. DoD has been essentially, pumping and treating PFAS contaminated water for a good 25 years or more. Tim has already pointed out, obviously, that the PFAS and PFOA are what's really driving the treatment technology. But if you look in the chat, you can see that obviously, depending upon your state, each state's got an individual set of PFAS contaminants that they're concerned with. And when you're on a DoD installation, there is actually an RSL for a PFBS contaminant that also has to be accounted for. Now, most of these others have relatively high discharge criteria or treatment goals in comparison to the 70 ppt for the combined PFAS-PFOA. As you can see, PFAS and PFOA, you can basically visualize these as the Teflon surface in your cooking ware. They're pretty stable. They don't have vapor pressure. They are essentially 100% soluble in groundwater. They have very, very low partitioning coefficients, so they don't stick to the soil. So when you go out and see these plumes are long and wide, depending upon how groundwater is flowing. The two contaminants, PFOA, PFAS, are very stable contaminants. They do not degrade biologically. Chemically, you have to really attack them strongly to even get them to degrade, and there's even some concern that they're not even really degrading. When you get to a design, so the PFOA, PFAS is relatively straightforward as the design. The design gets more complicated when you have to consider all the other co-contaminants that you may be with, as well as the geochemical conditions that you may be stepping into. And some of the classics are just like any other pump and treat system. It's the ferrous iron, the dissolved species that would precipitate in your GAC vessel. It's other VOCs that may be preferentially taking up GAC active sites so that the PFOA, PFAS are not being absorbed. And so those are the ones that you have to spend a little bit more effort on to make sure, again, your design is going to be successful. Hey, Tim, next slide. Are you pulling from the same ITRC report that Tim mentioned earlier? This is, I believe, an April 2020 report. It's very thorough in its assessment of what has been done, what has been attempted, and what has worked. I'm only going to focus on what I call the field implemented technologies. Those are technologies that are at full scale, at multiple sites by multiple consultants. And we're not going to spend hardly any time on the limited applications or the developing technologies. You can appreciate there is an awful lot of research. There's an awful lot of speculation, an awful lot of claims that are out there about what they can be done. But at the moment, it's really, again, a limited field of implemented technologies that have actually worked. The ITRC report has a great summary of all the other technologies that you may be interested in. And like I said, the only one besides GAC treatments, there is some chemox, but again, it's really extreme chemox that has some potential. And of course, there is still an awful lot of debate over how effective it really is. Ready, Tim, next slide. All right, so if you run into it and you're having to design a treatment system, the presumptive remedy for groundwater is granulated activated carbon, GAC, or ion exchange. Both have a long history of proven operating experience, lots of different vessels, or I'm sorry, lots of different installations that have designed this and have them up and running. These are very, again, I'm going to call it traditional designs, lead lag vessel designs, obviously with the GAC and ion exchange, particulate control so that you don't blind those vessels and plug them off is very important. And then the regenerated media is obviously sent off-site back to your ion exchange vendors and your GAC vendors to be thermally regenerated. There are concerns about the media and how it's being disposed in the life cycle for that spent media. Obviously, there are lots of concerns about solid waste containing PFAS going into landfills and how that is actually then leaching out of landfills, passing through the bottom liners, and then ending up as groundwater contamination. So there may be some concerns or some changes in how media is regenerated in the future. But again, it's a very straightforward GAC type design. Tim, next slide, please. So this, some design criteria for you just to get a sense of how much GAC you need. This is based upon Deb McDonald and her Wordsmith's design project. They actually did bench scale tests to at least come up with the initial GAC loading that they needed. And then, of course, they built a full-scale system at Wordsmith and operated it. Ganesh was the designer, obviously with a lot of Deb's guidance and support. So I would say when you get to design questions, definitely reach out to those two because they actually have the most up-to-date experience. So GAC is, again, it's all about influent concentrations to achieve that 70 ppt on the back end. The higher the influent concentrations, the quicker you will see breakthrough, and obviously this GAC consumption will go up significantly. This GAC consumption of the 0.2 pounds to 0.5 is based upon about 2,000 ppt on the influent. That's achieving, again, less than 70 on the backside. Ion exchange are the other media that you can use. The Camp Lejeune project is actually using a combination of both ion exchange and GAC. The ion exchange is acting as a safety polishing unit, and the GAC is again doing the bulk of the treatment. With that, ion exchange media is substantially more expensive, and it's priced accordingly to try and again be competitive with the GAC. But the key with the ion exchange is that you end up with smaller treatment units for the flow that you're dealing with, even though the consumption is a little bit lower too. All right, Tim, next slide. For soils, there's really only kind of two remedies here. Dig it up and put it in the landfill, or you dig it up and you try and wash it to remove that very soluble PFOA or PFAS, and then you end up with a treatment system to deal with, again, the washed water. Your landfill disposal is very, very site-specific. Some landfills refuse to take it. Others are more receptive to it. That's probably out of ignorance more than anything. But you really need to nail down your local landfill or the landfill that will accept this. There are several across the Southeast and Midwest that are accepting the material, and they again range from subtitle Ds to subtitle Cs. The soil washing and or stabilization again has been done. I don't really recommend the stabilization. That's basically encapsulating it in concrete. And there are definitely some long-term concerns about what will actually leach out eventually from that material. There are not soil criteria for the moment. Most of the soil criteria are derived from those drinking water advisories, so that you back up to them based upon some sort of dilution attenuation factor or DAF. Again, 20 is usually typical. Where you're trying to avoid, again, leachate that's above the drinking water standard that's hitting the groundwater. But at the moment, there are not soil criteria. And of course, there are some thermal incineration technologies that are out there. Obviously, ECC has a great experience in terms of thermal. I don't believe we have actually treated any PFAS material yet via thermal. All right, Tim, next slide. All right, Wordsmith. This is again a project that we have under our quals and experience. We were one of the very early on ones to actually have a treatment system. We actually designed it, we built it, and then we ran it until that contract turned over to another competitor. Deb McDonald was the PM, so when you need specifics, definitely reach out to her. But again, she was dealing with a fire training site that was running off into basically the local lake. The regulator was Michigan, actually had a son who had medical issues and was quite passionate about making sure that this was treated. And of course, the Air Force is the one that stepped up and said that they would put the treatment system in place. Deb's design included everything from soup to nuts from beginning to end. They had to do pump tests to ensure hydraulic control. They had to do treatability tests to size the vessels. And then they had to do the whole mechanical, electrical, civil design. They had to do this under an expedited time frame. And of course, in the winter months, just to make things fun. So again, a really great qual for us to try and use with other projects. All right, next slide, Tim. All right, just some simple components that you can see here for the treatment system. There were 7 extraction wells, 240 GPM. She had 2 GAC vessels in series, so again, a lead lag configuration. The treated water was actually not discharged to a surface water body. It was actually re-injected up gradient, and James Gatherer is the one that did the modeling on this to make sure it worked. And when the contract turned over at our end, we had treated over 200 million gallons, and of course had meet the discharge criteria for, at least for Michigan, was 60 ppt at that point. All right, Tim, next slide. Actually, you can go 2 if you want. And I'm turning it back over to you.
Okay, bear with me here. All right, thanks, Mike. Appreciate that. I'll be talking now about disposal, and a lot of what you're going to hear dovetails really nicely to what Michael was just talking about. What we're seeing are 2 ways to handle or dispose of PFAS that we generate through our various types of investigations or response actions. The first is landfilling. Disposal of PFAS largely remains unregulated. However, as Michael was previously saying, there's becoming some long-term consequences with the management of PFAS and landfill leachate, and that has gained attention, and a lot of landfills are now refusing to accept contaminated soil or groundwater that would be generated from various types of remediation programs. So I think doing some due diligence before you get to this point in a project would be a prudent approach to follow. The next disposal option that I'm going to talk about is incineration. And again, this is related to what Michael was saying. It's essentially, since these compounds are so stable, breaking them down is problematic. You need a high level of heat to get that accomplished. But even when you do that, what the literature is suggesting is that there's incomplete destruction resulting in the formation of smaller compounds, or what we call in the incinerator world products of incomplete combustion. And a lot of those PICs have not been researched, and they could, be a potential problem going forward. Anytime, at least in my experience as my academic background is in public health, but anytime you talk about incineration, there's 9 times out of 10, or maybe 99 times out of 100, public perception concerns. So, that is not exactly helping the incineration disposal method. But ultimately, there's more study needed. And what this source here, if you have time to visit that, they'll speak to that in a little more detail. So I'd encourage you to check into that as well. So we've been through pretty much the investigation, what PFAS is, what the regulations are, how do we treat it. And now we'll briefly talk about the DoD's position. In other words, what do they want us to do as their contractors? So their position is essentially summarized here. Oh, hold on, let me go back one. They had issued a memorandum in 2019 that clarifies their approach. And it's essentially saying site could require a remedial investigation depending on the levels you see, or it can proceed to site closeout. So that directive also meant that we are to treat PFAS, again, PFO and PFAS, in the same manner as other contaminants of concern within the DERP. And there is a reliance when you're doing a remedial investigation to determine if action needs to be taken or a site can go to site closeout. There is a need to demonstrate risks, and you do that by completing what we call a site-specific risk assessment. And that's essentially used to determine if remedial actions are required in accordance with CERCLA, the DERP, or the National Contingency Plan. Once an MCL comes out from the federal government, that whole paradigm could change, but we'll have to wait and see. So that concludes my piece of the presentation. I'm going to throw it over now to Doug McClure, and he's going to talk about what we're seeing. He's going to summarize our experience and what we're seeing as our current and upcoming opportunities. So Doug?
Thanks, Tim. Go to the next slide. So Tim and Mike talked a little bit about the history of PFAS, chemistry, some of the treatment technologies, and I think they set the groundwork for the fact that this is a big deal. It's a big deal everywhere, but specifically for the DoD because of all the firefighter training that went on and the chemicals that were used. So there's a lot of opportunity out there. We've been fortunate so far to have some experience in this area. They talked about Wart Smith Air Force Base, having this experience dating back, 6 years ago now, where we designed, built, and operated a PFAS treatment system. One of the first that I'm aware of for the Air Force. Was a great experience, and that project went extremely well and was rated very well by the Air Force. And as Michael alluded, it gives us an opportunity to leapfrog to get more work. Very similar work because of our experience there. We've also touched PFAS on some of our work for the Army over at Aberdeen Proving Ground. Rob Wassman and his team have been working there for quite some time and have had some experience with PFAS sampling there. Under the IRMA contract, we're seeing some opportunities come up. I know that we were able to negotiate with Arcadis, since they have been doing a nationwide program of preliminary assessment site inspections for the Army, and we had been working at some facilities where they were doing that work. We were able to negotiate with them to get us involved in their PFAS program. So I believe that's ongoing at Milan Army Ammunition Plant and at Fort Knox. And apparently, I believe with Fred Santos's project on the New England group, PBR, we were asked to do some PFAS sampling up at New Boston Air Force Station in New Hampshire. So we've got some experience under our belt, and I just see it popped up here. We also are getting experience at Camp Lejeune under a project through the construction group to deal with some PFAS impacted groundwater. So we continue to grow the resume, which is important because this is obviously a big issue going forward. Next slide, Tim. So we have some current opportunities. I think, Tim, you touched on this one here at Fort Hunter Liggett and Joint Base Lewis McChord. We just won a PFAS RI, which is a big deal because, as Tim mentioned, it's beginning for the Army and other parts of the DoD where they're looking at conducting remedial investigations at sites where they know they have confirmed PFAS releases. So this is one of those installations. A great win for ECC and another opportunity for a great resume builder there. We are in the middle of submitting a proposal to DLA at one of the defense fuel supply points up in Verona, New York for, believe it or not, most of the work on that contract is the potential to do some additional PFAS investigation. They did have a PFAS release there. It was a documented release with the New York State DEC. And apparently they're wanting the capability to do more just in case the state comes back and asks them to do so. So we're in the middle of putting that proposal in. I think it's due in another few days. And then most recently, we were awarded a contract with AFCEC, the Air Force, for a bunch of BRAC sites up in the Northeast in New York and New Hampshire and Maine. And that contract, although it includes a lot of traditional contaminants, there is a huge PFAS focus, especially at Pease Air Force Base in New Hampshire, where they've had documented releases and are dealing with treating PFAS in drinking water. And so there's a lot of work to be done there at Pease and potentially at other locations at the other BRAC sites. So we have some current contracts now where we're building and continuing to build our PFAS resume. Next slide, Tim. And then just a list of some other opportunities that we're tracking. One of the things that we've been seeing with the Army Corps is the AFFF, the aqueous film forming foam, which is the genesis of a lot of the problems. Especially the Air Force has been replacing their AFFF systems, which are used in hangars for fire suppression. And ECC's bid a couple of those, hasn't been successful, but we are figuring out how best to do that going forward. We expect we'll see more opportunities to do that under one of our Huntsville contracts. Second bullet here, Army Environmental Command, that's on our IRMA contract. Rob and his group there again, we're aware that the Army is ramping up in FY21 to look at possibly regional approaches to investigating PFAS releases. That could be multiple installations, similar to what the Air Force does in their ORC and PBR program, whereby we would be most likely doing remedial investigations at multiple Army facilities. We are looking at some of the contracts that were recently awarded. We did win a Kansas City PRAC contract, which it appears that a lot of the Corps districts are now wanting to have the capacity to assist with PFAS work, and they're using their RAC remedial action contracts and their ERS environmental remediation services contracts to do that. So we're seeing that coming up. We bid and won the PRAC with Kansas City. We're waiting to hear on Omaha. We also have one with St. Louis, although that might not focus on PFAS. There's one for Mobile District where we're supposed to be bidding in the next month, and so those will be important contracts. I know we're running late on time here, so just a few others here. One I want to touch on is that one with PACAF. Michael and Tim talked about potential impacts to soil up at Eielson Air Force Base in Alaska as part of the F-35 build-out. They have encountered a lot of PFAS impacted soil for their Milcon construction program. They're in the process of setting that soil aside and have approval by the Alaska Department of Environmental Conservation to stage it to the point where they have a large quantity, and they're going to look at some type of potential thermal treatment for that soil. So the takeaway here is that the DoD recognizes that they're going to have to deal with PFAS impacted soils, and some of these installations where they have a lot of it, they may look at alternate methods to procure and get contractors to come in and come up with more innovative solutions to do so. So we continue to look at all these opportunities with the Army. The last one there is a potential for call it a grant, if you will, with the Navy to maybe prove out low temperature thermal desorption, working with Shovik on that to see if we can get a grant and see if we can make that work for the Navy. So there's a lot of work to be done in the future. And as you can expect, we've been around through a lot of the other types of contaminants. And in the Superfund process, the CERCLA process, nothing happens quickly. So we're at the beginning stage here, and there's at least another 10-year cycle to get through all of this for PFAS. Thanks, Tim. I think I've covered it all.
Yeah, thanks, Doug. So that wraps up our presentation today, everybody. Let me just get to our next slide here. I appreciate everyone taking the time. If there are any questions, now's the time. But before that happens, Natalie, do you want to throw the quiz? How do you want to do this quiz thing, or what's the plan there?
Yeah, of course. I am sending a link out in the comments box right now. So if you click on that link, that should take you right to the quiz for a knowledge check. They're just 4 questions. It should take you pretty quickly to do that. If you have any trouble, just let me know, or you can access Talent LMS by logging in, and it should show up under live meetings in your learner dashboard.
Great, thanks, Natalie. Okay, does anyone have any questions, concerns, clarification needed?
I got a question for Michael. Given the partition coefficient and maybe the hesitancy to use thermal, has anybody looked at soil washing? Soil washing coupled with carbon, coupled with ion exchange or something?
Yeah, that's what I talked about is the soil wash. That's
Oh,
one
yeah.
of the field demonstrate. Yeah, it's one of the field demonstrated for soil.
Should we look at that for
landfill.
Ilsen? Should we look at that for Ilsen, or some demonstration study somewhere? We can talk about it offline.
Yeah, the only thing I'm contemplating here, August, is I'm not sure what has been done and what hasn't been done. So it would just take me a little bit just to go back to that ITRC and just see if there is another soil wash. I'm pretty sure it was in the field demonstrated category of being done at several places.
We should be sure to understand that pretty well, because whoever, I think you said it, or whoever said it, there's going to be a lot of reluctance for thermal. And maybe soil washing would be a more acceptable alternative. Anyway, something to think about.
I don't know what Shovik and Doug are chasing, but obviously the indirect thermal is the one that really probably has the advantage. The direct thermal with an oxidation unit on the back is going to have all those paradigms associated with it. The indirect is actually a pretty nifty way to go about this.
Yeah, we need to continue to look at that. Okay, thank you.
Hey,
you guys did a really good job.
Hey, Mike, what about in situ thermal like ERH or TCH? Would that work, or would the temperatures not get high enough? I think you had 1100 degrees Celsius.
Yeah, the resistance heating can get you up there, but even in the resistance heating, Paul, they're still only getting into like the 600, 700 degree range, which is really cooking. And you're just not high enough to get this stuff to desorb. You really got to crank it up into, like the 1800s to 2000 to get it to desorb. Gotcha.
And I had one quick question for Tim. What are the ecological effects of PFAS? I know the human health effects it's a carcinogen.
Yeah, so there are. It depends, I think, is the easy answer. It depends on the species you're looking at. What I can tell you is that the available literature for ecological screening levels or values is relatively Spartan at this point in time, but there is work being done to develop various screening levels. But we do see it, as I'd mentioned by my experience down in Alabama, 15, 20 years ago, that it does accumulate in tissue. So there is a concern there. It's just not fully understood for ecological exposure routes just yet.
Okay, thank you.
All right, and Tim, I have a question. This is Pam. Are the laboratories able to have low enough detection limits for compliance purposes? Like some of the 70 is a total, so they'd essentially have to have, so let's say there's 10. I don't know how many there are, but there's 10 that they'd have to be cumulative of their detection limit to show that we're below the 70. And I guess, are there any issues with the lab providing those detection limits?
Not anymore. The procedures have really, number one, improved, and number two, really come down in price. We're actually starting to work on a QAP right now where we'll be diving into that a little deeper. But I think what I saw is labs are getting into the single PPT levels for these compounds at this point in time.
Okay.
Any other questions? Going once, twice. Okay. Well, thank you, everybody. I appreciate the time and the interest. And like I said at the beginning of the call, if there's anything you guys want to talk about offline, certainly reach out. And I'll speak for Michael and Doug. We'd be more than happy to help you guys out, answer any questions you might have. So thank you.
Thanks everyone.